I think we'll get going because we're sorry about that. The pizza was downstairs, and some of it got eaten. But they only delivered like a third of what this was, so the rest of it's on its way. So if you're still hungry, there'll be lots of food downstairs. And also, we'll probably take bread opportunities because we can get another beer because they're free. So welcome. Big thanks to Skills Matter. It's the first time we've been here. We too big for our little office in Old Street. This is working, is it?
It's working.
Is it working? Is it? Yeah, welcome. It's quite disruptive in that little office, and we like yours to be sitting here. So this is those guys. Big thanks to Skills Matter. Much appreciated. I have to say, because Amy will crucify me if I don't, that Red Badger is hiring. And up the stairs with PMs and UX and design. So come join us, it's great fun. Yeah, tonight we've got Tom, who's going to do the first talk, and we've got Ben Ford after that, so we'll have a break between the two. So let's go. Don't forget to tweet. Can you hear me?
I lost the slides for some reason.
Oh, you lost one here. We need to. All right.
Yeah, all good.
Cool. All right. Hi. My name is Tom Duncalf. I'm a freelance software developer. I mainly work with JavaScript and TypeScript and React and things like that. But today I'm going to talk about some functional programming fundamentals. So the thing I'm going to talk about is sort of the basics, so pure functions, type signatures, first-class functions, and then currying, composition, functors. And I was going to talk a bit about monads, but I don't know if it'll be time to see. So these are kind of like fundamentals of functional programming, but I've always felt like they're explained in quite a theoretical way, and it can be hard to grasp like what purpose they actually serve or even to understand them. So that's what I thought until I read this book, which is called Professor Frisby's Mostly Adequate Guide to Functional Programming, and it's a lot better than the title suggests. It kind of introduces functional programming concepts from the basics using JavaScript as a language. And it's really good. It kind of assumes no knowledge and builds you up to a point where you understand what a monad is, which is quite impressive. So this talk is like heavily based on this book, and I'll be showing code examples in JavaScript to kind of show that you can gain from functional programming even if you're not using a purely functional language. So let's get started and define what a pure function is. So a pure function is a function where given the same input or inputs, you always get the same output. And that means there can't be any dependence on anything like external to the function arguments. So if we look at an example here of this function, it's going to take a password and tell us if it's greater than or equal to a certain length. But because it's dependent on this value min password length, which is outside the function, we can't say it's pure, because if that value changes, then the result of the function changes. So we can't say that the same inputs return the same output every time. It depends on something external. If we want to make this function pure, we'd make it so we pass in the minimum length as one of the function parameters, and now we can say that for a given combination of inputs, we always get the same output. And there's another part of being a pure function, which is that we can't have any observable side effects. A side effect is we can define it as any interaction with the world outside of our function, and that's things like making a request, interacting with a database, printing something, changing the file system, anything outside of a function. And like a quote from a book there is that these side effects, so anything interacting with the outside world, is a primary cause of incorrect behavior in programs because it's unpredictable by its very nature. So you're probably, well, if you're new to functional programming, you're probably questioning how you can program without side effects, because a program which doesn't do any of this stuff isn't going to be very useful. And the answer is that we can't, but what we can do is aim to contain those side effects and execute them in a controlled manner, and functional programming kind of gives us the tools to do so. And so why do we want to write pure functions? Like, what are the benefits of it? Well, I think for me, the primary one is that it's easy to reason about. So if you know that a function is only going to take these certain arguments and its output isn't going to affect the world outside of it, then you can use that function and think about what it's doing easily without having to think about how it's going to affect the outside world. They're also trivial to cache because it's just you could just store a mapping from input to output. You know that it's never going to change. It's a technique called memorization. They're easier to test because you don't need to sort of mock the environment outside of the function. You just give it certain inputs and certain outputs. But easy to parallelize because you're sort of not giving shared resources. And they also meet the mathematical definition of a function. And all of this sort of functional programming stuff I'm going to talk about is backed up by a branch of mathematics called category theory. And there's not time to go into any of it, but if you read the book, it does actually discuss how these things map to category theory. But just to mention, like, this is sort of, that's a mathematical definition of a function, and that kind of enables all the other stuff you'll see. So I'd like to introduce type signatures. So a type signature just specifies what types the inputs and the output of a function are. So type is something like a string or a number object. Obviously, if we're looking at JavaScript, there's no type checking. It's not a statically typed language, but we can still gain some benefits by documenting the types in our programs and by thinking about things in terms of types. And when you look at functional programming libraries, you'll often see the functions are described in terms of the types they take in and that they return. So let's look at a few examples. They're called Hindley and Milner type signatures, I believe. But so here's a function which takes a string and it's going to return a number. And so we write that as string length, colon, colon, string, arrow, number. So that's just saying function string length, it takes a string and returns a number. Here's another example which returns an array of strings. So the difference is we've got square brackets around string. That's how we indicate that something's an array. So here's a slightly more complicated function in that it takes two inputs. So you can see it takes a string and a string. It's going to return an array of strings. And you'll notice that we don't do anything to signify that refers to our input arguments, and the last one is the output. So function always has one return type, so we know the last thing is the return type. Anything before that are arguments for the function. And this kind of makes a bit more sense when you learn what currying is. Here's a function which takes a function as one of its arguments. So you can see here we indicate that as using the brackets, string, arrow, number. So we're saying it takes a string and a function from string to number and returns an array of numbers. And then finally, here's an example of a function which is polymorphic, so it will operate on any type. So we're saying it takes an array of type A, a function which goes from A to a B, and it's going to return an array of type B. And A and B could be any type, string, number, you know, and they could be the same type, they could be different. So I'd like to define what a first-class function is, because that's kind of fundamental to the way we can work with these functions. So in a language where functions are first class, of which JavaScript is one, a function is treated like any other data type. So that means you can pass functions as arguments to other functions, you can return functions from functions, you can store them in variables, and you can store them in arrays, and that function isn't actually going to do anything until you invoke it with brackets in the case of JavaScript. So here's an example function which is going to return a function. So here we're giving it a string and it's returning a function which is then going to return another string. So you can see the type signature. It takes a string and it returns a function from a string to a string. And we can see that if we invoke it once, we get that function. If we invoke it again, we actually see the result of that function. This also has the effect, which I learned from this book. I haven't really thought about this. So if I've got this code here, take an array of passwords, and we're going to see if it's a good password. Because the function name is just a reference to a function, we actually don't need the enclosing bit of password here. We can just say map and give the function name, and then when it gets applied with brackets, the function is going to get called. So it kind of saves you a bit of boilerplate. So like this obviously gives us less code, it's potentially more readable, and functions which can accept and return functions gives us quite a lot of flexibility in making our program behave in interesting ways. And it also reduces the need to name things. So like in this example, I've got this intermediate variable called password, whereas when I use the function in a first-class way, that's gone. Which kind of allows us to write code in a more generic way. And this is a theme you see through quite a lot of functional programming stuff, is like writing generic functions and using them in a way which makes them domain specific. So next, I'd like to introduce the concept of a curry function. And a curry function is one which can be called with fewer arguments than it expects. And if it's called with fewer arguments than it expects, it's going to return a new function which takes the remaining arguments, which is better to see an example of. So here we're defining a function called add, and that's going to take a x, which is a number in this case, and then return a function which is going to take a y, and then it's going to return x plus y. So if we look at how that would work, add 1 is just going to return a function which is waiting for y, but the value of 1 has been kind of pre-filled there, so we've given it an x. So if we call add 1 and then call 2 on that, we get back 3 as you'd expect from calling x plus y. And we can take advantage of the first-class nature of functions by storing these sort of intermediate functions in variables. So here I've defined a function add1, and I've stored that into a variable or a constant called add1, and another function add10. And then I can use those as functions, like add1 to 2, add1, add10 to 2 gives me 12, as you'd expect. So one thing to note here is that in JavaScript, functions aren't curried by default. So in some languages, every function you write will be curried, and you can call it with less arguments and get back what they call a partially applied function. In JavaScript, that's not the case. But if you use Lodash or Ramda, which are kind of the two big functional programming languages in JavaScript, they include a version of curry, which will work on a function with any number of arguments. So you don't need to write every function the way we saw with that add function. And here's how you'd write a curried add function using Ramda. So we include in Ramda, require in Ramda. When we just call add.curry, we give it a normal function, where we get back a function which can be called with a single argument, and it's going to give us back another function. Or we can call it twice, which will give back the result, or we can call it in a normal way, and it'll do the same thing. And it's worth mentioning that all the functions in Ramda and in the FP branch of Lodash, so like not in the normal Lodash, but if when you require something, you put Lodash/FP, they're curried by default, so any function you use from there can be called with less arguments than it expects. And the data arguments, the thing we're operating on, come last. So this means you can kind of pre-fill the function easily. So here's an example. There's a function in Ramda called test, which will take a pattern, a regular expression, and a string, and it's curried. So I can really easily define a function. Is Gmail address here, and I'm just calling r.test with one argument, which is regex at gmail.com, and I've got a function that I can use to test that an email address is at gmail.com. If the arguments of a function will be the way around, which they are in normal Lodash and underscore, and there's actually a talk by the guy who wrote the talk that I mentioned about this called Hey underscore, you're doing it wrong. You couldn't do this as easily because you can't just give it, the input string is the thing we kind of want to pass in last. So it's good to make use of one of the libraries which kind of gives you this functionality. Why do we want to do currying? So as we saw there, it gives us the ability to really easily make a function. And what this means is we can reuse generic functions in a domain-specific way really easily. So like my Gmail address example, I've got a function which detects the Gmail address, but I've not had to go through a sort of ceremony of wrapping in a function and giving this intermediate name here. You can see that if you use the pure ES6 syntax, then the kind of syntactic overhead of it is a lot less, but still you've done away with the need to name these intermediate variables, and that can make you a lot more likely to reuse functions rather than writing a new one every time. But where currying really becomes useful is with composition. So for me, composition was kind of where I started to see almost the power of working with first-class, pure curried functions. So let's take a look at what it is. So compose is a function which will take two functions, f and g, as arguments, and it will return a new function, which is going to take an argument x, and then it's going to return the result of f brackets g brackets x. So that's, you're going to call g on the value x, and then you're going to call f on the result of that. And this actually maps to a mathematical definition of function composition. Again, not got time to go into that, but if you read the book with more about that. So let's see like how it actually looks. So Ramda has got these functions add and multiply, which operate exactly like the infix operators in JavaScript, but they're written as functions, so we can curry them and we can use them in this way. So add 1 and 2 is 3, whatever. So I can create a function here called double plus 1, which is going to double the number and add 1 to it, just by calling compose, and then we're going to compose. So in this case, g is r.multiply 2, and f is r.add 1. So we end up with the equivalent of calling multiply 2 and add 1. So you can see here that if I call that on 3, I get back a value of 7. If I call it on 5, I get back a value of 11. You can sort of think of a value being piped through this from right to left. So it kind of becomes clearer why this is cool if we look at a slightly more involved example. So let's say we want to return the average length, how can I read this one? Average length of any words longer than 3 characters in an input sentence, and we're going to format them somehow. And imagine we've got a function average, which is going to take an array of numbers and give us back the average, and we've got a function which is going to format a number for us. So without composition, a first pass at writing this in JavaScript might be like this. So we can split the words, map over them to get their length, filter out anything where the length is less than 3, get the average, and return it. So that's like quite readable code. It's clear what it's doing, but it's a lot of code for quite a simple thing. So we could reduce that down by doing away with the intermediate variables. So here's the same function, but we're doing it all in one line. But I think we can see that the clarity of it probably suffers here. So if we follow that through its execution, what's happening is we're splitting the input, we're mapping over it, we're filtering it. Then we're going to average, and suddenly we jump from the end back to the beginning because we're going from object methods to functions, and then we're going to format it. So it's kind of, you get used to looking at code like this, but it's actually not that easy to read. So we could rewrite that using the functional versions of map and filter, and that's maybe better, maybe not, but you end up with this kind of cascading bracket thing, which kind of discourages you from writing code like this. So with composition, we can rewrite this in this way. So we've just got one line with a clear sort of pipeline from right to left. And if we follow this through, if I pass this sentence into my compose function, first thing that's going to happen, we're going to start from the right, pass the value in, we're going to split it into array of strings, and then we're going to map over that and get the length. Then we're going to filter out anything which is less than 3, then we're going to work out the average, then we're going to format it. And so you've got this really clear sort of pipeline going from right to left, and I'd argue this is definitely more readable than that, and possibly more readable, or certainly more compact than the other version we saw of the intermediate variables. One thing I should mention is this demonstrates something that's called point-free style that you probably hear of when you look into functional programming. What that means is we're never mentioning the name of your data we're operating on. So if you look at the JavaScript version, we've got a variable called input. We look at the composed version, we never have the equivalent of that. So point-free means that you don't mention the data you're working on, and it's kind of a good test of how functional your code is, as I understand it, but some code is going to suffer in clarity if you try and write it that way. So it's a kind of tool to use when it suits the code. And again, composition, I think it encourages reuse and combination of these small, generic functions together. But it's not perfect. So I saw that and I thought this is pretty cool. But there's a catch. So for example, how do we handle potential errors in our code? So if we define a function called head, which is going to take an array of somethings and return the first something of that, and we call that the list 1, 2, 3, then we're going to get back string 1 as we'd expect. So I could create a composed function which is going to take a head of a list and then it's going to reverse that. And if we give it an array like that, we're going to get back ENO. And so far so good. But if we give it an empty list, so if we call head an empty list, if you call square bracket 0 on that, you're going to get back undefined. We then try and put that through our compose function. We're going to get an exception because r.reverse, random's reverse function, is calling the object's length property internally and an undefined object and a length property. So we don't want exceptions in our code. We could handle this by wrapping reverse in a null check if we wanted to, but that's kind of ruining the compactness of the code. We don't want to have to wrap every function in a null check where something might return a null. So the solution for this problem comes from something called functors, I don't know. So let's introduce something which we're going to call a container. And what this container does is just takes a value x and stores it in a variable, an instance variable, which we're going to treat as private. So we're never going to access this underscore value. And we're also going to define a static function called of, which is going to take a value and put it in a container for us. So we can create a container of 4, and we get back this object which has a value of 4. We'll call it container of 4 because that's easier to read. We can put hello world there, and we'll get like a container of hello world. We can put whatever we want in there, and we'll just get a container of it back, which is pretty useless, to be honest, because what's the good in having a number in a container? Let's add a map function, which is going to allow us to apply functions to a value inside there, just like array map allows you to apply functions to the values inside an array. So map is going to be an instance method of this class you'll find here, and it's just going to take a function, and it's going to return a result of calling that function with a container value, but wrapped back in a container. So what we can see here is we define 4 in a container, and if we map add function to add 2, we get back a container of 6. So here we can apply functions to our container without it ever having to leave the container. And we can map as many times as we want. So we can, here we've got 1, 2, and we're going to take the head, and then we're going to reverse it, and we get back ENO again. And you just change maps could go on indefinitely. You're still keeping the value in its container, and it's just in one container. And this, it turns out, is what a functor is. It's a type that implements map, and it obeys some laws, which we don't have time to go into, but these are kind of part of the mathematical foundation behind it. well, like, what's the good of this? What's the point of putting a number in a container just so we have to call map to interact with it? And it turns out the answer is that we're abstracting function application. So rather than running a function directly on a number, we're asking the container to run that function for us. And if we think that we can redefine that map behavior, this allows us to do some quite useful or powerful things while calling map. So let's introduce a function called maybe. And maybe the basic top two parts of it is exactly the same as our container, it's just storing a value inside it. Where it gets interesting is if you look at this map method. So when we ask an instance of maybe to map a function, it's going to first check whether its value is null or undefined. If it's not, then it's just going to execute the function and wrap it back up in a maybe and give it back to us. But if that is null, it's just going to bypass executing the function and give us back a maybe or null. So this, you can probably imagine, it gives us like the ability to potentially work around our problem with nulls and composition. So a maybe with a sentence in it or a string, and I call reverse on it, that works exactly the same as our container, it puts it back in the container. But if I take a maybe or null and I run reverse on it, if you remember, reverse blew up with an exception in the previous example when we just called it directly. Because it's wrapped in a maybe, is nothing that's going to return true, and so we're just going to get back a maybe of null and we've got no exception. Whereas if we did this to our basic container, because it's just applying a function, we get back an exception. So maybe is actually taking care of null checking for us, and we're not having to wrap each function in a null check. And the way you typically see this used is as a return type of a function which might fail to return a result. So if we think about a head function, which we know it might fail to return a result, so what we can do is create a function savehead, which is going to do the same thing, but it's going to wrap it in a maybe. So if that value is null, we'll get back a maybe of null. And now you can see if I do savehead for this, I get back a maybe of 1. And if I do it on empty this, I get back a maybe of null rather than defined. So this gives us a sort of type safety, because it forces the calling code to sort of acknowledge and handle this null case, because we can only get a value inside this container by calling map. If we try and call it directly, we'll either get back an error or just nonsensical results. Like in a strongly typed language, you wouldn't be allowed to do that, I guess. But in JavaScript, we don't get back the result we expect. So if we want to do something with that value, we have to call map, which means we can't end up in a situation where we're going to get exceptions because of nulls, which is quite clever. And we can compose these functors together. So we can compose maybe together just like we would do with normal functions, except we have to use map to sort of go inside the container, if you like, and operate a function. So here we've got a function which is going to take the head of a list, reverse it, and convert it to uppercase, which is really useful. But we can give it a list of strings in, we get back a maybe with case reverse string. If we give it an empty list, rather than getting an exception, we just get back a maybe of null. So you can see, but because we started with null, that null just propagated through the function, and at no point did we have to worry about the fact that it was null. And you can imagine sort of arbitrarily long chains of functions where we don't have to worry about things being null. And function being called like reverse or to upper doesn't have to care about the fact that it's operating on a maybe, because we use map, which does what's called lifting the function kind of into the world of the functor, if you like. So I think that's quite cool, because that gives you a kind of type safety even in a language like JavaScript. Next I'd like to introduce a functor called IO. So before I introduce it, I'd like to sort of go back and remind you that a pure function can't have any side effects. But there's kind of a trick we can do to make a function which has side effects be pure. And that is to wrap the function inside another function, delaying the execution of it. So here I've got a function which is going to get a value from local storage. But what I've done is I've wrapped it inside another function. So now this means that if I call this function with a value, rather than getting back that value from local storage, I get back a function which is going to get that value from local storage. And then if I call that function, I get the value. So we can say that we always get, for our get from storage function, we're always getting the same output for a given input. It just so happens that that output is a function rather than a value. So we've kind of technically made our impure function pure, but it feels a bit like cheating because it's not really all that useful. But we can make use of this to kind of manage side effects better and to contain them. So IO is a functor which acts much like maybe a container. The difference is that when we use the of method to create new IO, what we give it is going to put it inside a function before giving us it back wrapped in an IO. So what this means is that we're basically getting the equivalent of what we just saw there. So if we give it something which is impure or has a side effect, it's going to wrap it in a function. So it becomes, technically, we can say it's pure. So if I put window location href inside an IO, window location href is impure, right? Because it comes from the outside world. Its value is changing with time. So I do that, and I get back something which has got an underscore value, which contains this function. And the function looks a bit like this. It's just going to return window location href. And then I can call that and get back google.com or whatever. But the point here is that if we were returning this from a function, we'd put the onus for calling the side effect onto the calling code rather than our code. So you can think of our kind of code as pure, and then at the end, you're triggering the side effects. And because we're kind of directly calling this value, that looks a bit messy, so we can rename this to unsafe perform IO. So then if you want to get the value of this thing, which is unsafe, you have to call unsafe perform IO, and you're kind of being made aware of the fact that what you're doing has a side effect. You should think about, what the repercussions of this side effect, I guess, when you want to call it. Where IO gets quite clever is in its implementation of map. So for IO, when we give it a function to map, what it's going to do is compose that function with its value, which is the original thing we want to get, so window location href. We're composing that with the function we give it. So what this kind of means is we're creating like a chain of composition which isn't actually going to execute until we call unsafe perform IO. So like here we've got our current URL IO, which has got window location href in it, and then we're going to map reverse, and we're going to concatenate a string reverse URL onto it. And internally, what you can visualize is we've kind of built up this composition chain here, where at the bottom we've got a function which is going to return our thing which has a side effect, or call our thing for the side effect. And then we've got the other functions on top of it, and that chain isn't actually going to occur until we call unsafe perform IO, at which point it's going to execute the side effect and execute everything else we put on top of it. So it's quite neat. You sort of think of it like a kind of domino rally, and like you build up all the dominoes, and then at some point you sort of push them and go. But you're putting the emphasis on like the person calling it to decide when that should happen rather than doing it immediately. And yeah, so this enables us to control side effects. It's certainly like a basic way of doing it, and there's lots more ways of seeing functional programming. But it helps us out, and it also shows the fact that this function is going to have side effects in the return type. So much like maybe told us that this value might return a null or a bad value, IO is telling us that this function is going to have side effects, and so when you call it, you're aware of that. And there's lots more functors, and I've not time to go into them or into any more detail on some of those. Like if you look at maybe, you'll see that it's actually implemented a little differently to what I showed there, but that's kind of an easy way to understand it. I would like to just show you briefly one called task. So I'm not showing the implementation of this, but task is a functor which we can give it something which is going to do something asynchronously, and we can call either reject or result. So we've got two callbacks we can call, and then we can compose as normal, so we can read file, split it into lines, get the length. And then when we want to actually execute this, we call fork and give it an error callback and a success callback. And you might be thinking this looks kind of familiar, and really it is, because a promise is very similar to a function or a monad, with the exception that instead of calling map, we're calling them to chain the things together. And also, there's not a way to defer execution of a promise in the same way there is with fork, because if I do this with promises, as soon as I finish this chain of thens, that's going to execute. But otherwise, it's pretty similar. So you've possibly been working with functors or monads without actually realizing it all along. How long have I been talking for? Should I go on to monads? It's only short. Okay, I've not practiced this bit, so forgive me. So this is a very basic introduction to monads, and there's a lot more to it. But when I sort of read this, I was like, oh, it's not as complicated as it's made out to be, perhaps. So functors are great. One thing we'll find though is if we're dealing with nested functors, our code gets a bit messy quite quickly. So here we've got a function saveprop, which is going to get us a property of an object, which might return undefined. So we're going to return maybe for that. And then we've got savehead from before. We can redefine that into the saveprop. So here, if I want to get the address property and then get the head of that, so it can be an array of addresses, and then I want to get the street property, you can see we're having to map once to get inside the first maybe, and then we're having to map twice to get inside the second maybe, and the result is 3 maybes deep, which is kind of crazy. So if we follow the execution of this, we call saveprop addresses on this, we get back an array of addresses wrapped inside a maybe, and then we map savehead, and we get back the first element of that wrapped inside another maybe, and then we map inside that and do saveprop again, and we get 3 maybes deep, which isn't great. And if you've got IOs, you'd have to call unsafe perform IO 3 times in a row, which it's not great. So if we introduce a function which we'll call join, what join's going to do is essentially remove a layer of functor. So if we have 2 nested functors of the same type, we can remove one of those layers without really worrying about the effect of doing that. So for maybe, we're just going to check whether it's nothing, and we either return back maybe of null, or we return back with value which is inside that maybe. Or for IO, we're going to call unsafe perform IO. But what's important to note is we're not actually triggering IO there, because we're 2 levels deep. So like here we've got an IO of window location href. When we join that, we just do away with a layer of it, but we still don't trigger the side effects until we call unsafe perform IO on it. So this, it turns out, is kind of the definition of a monad. So it's a functor which defines a join method. So it kind of tells you how to chain 2 of them together. It has an of method, which is what we use to put things inside it. And it obeys some laws, which again, I'm not going to go into. So now we can take our example, which had all the nested maybes. And if we will just define a function join, but we can use in a functional way. So it's going to take a monad as an argument, and then it's going to call its join method. Then we can refactor our code like this. So rather than the nested maps, we're just doing join, and we can step through that. So we get safe property to get the addresses, and we get like a maybe, and then we get safe header back, and we get 2 maybes. But we want to do away with one of those maybe, so we call join, and then we go back to 1 maybe, and then we get a property, and we're another maybe deep, and then we join, and we're back to 1 maybe. So the return type of this function is kind of same now. It's just a maybe string. And it turns out that this operation of calling map and then calling join is so common that it's abstracted into a function, which in this instance we call it chain. In languages like Scala, this is called flat map, and in Haskell, it's that little fella, I believe. I don't know what you call that one. But what chain is going to do is call map and then call join. So we can then actually refactor our code further, and these map join combinations can just be converted into chains, and then we've sort of dealt with the fact that we've got multiple layers of functors, we've got multiple layers of maybes here, but we're still just getting back a single maybe. And that's kind of a simple version of what a monad does. When you think about the fact that a monad or a functor or a monad can represent things like asynchronous I/O or something which has side effects, it becomes quite powerful when you think it's defining how you chain these things together. And that's, I guess, where the power of monads come in. So I'm not really about that. But so just to summarize, like what I sort of showed you, hopefully, is that some of these concepts don't have to be as theoretical as they're sometimes made out to be. They're useful even without understanding the mathematical foundations behind them. But it's nice to know that they do have these kind of mathematical foundations behind them. And we can kind of build up a powerful toolbox from these little tools like compose and using first-class functions and what have you, which enables us to write quite like elegant, clean code, which is compact, but it's also easy to understand, and it follows known rules. And it's backed up by those mathematical rules. And we can even gain advantages without using a pure FP language. So like JavaScript, it's not a strongly typed language, for example, but we can still, I think, gain some of the benefits of working with these functional concepts. And if you want to know more about it, I really recommend reading the book because it's free and it's very good. And there's some links on here, including a link to these slides, which is much good, because that's and that's it. So has anyone got any questions?
You can go back to your monad slide, or maybe slide.
Yes, very quick. Okay. Which bit do you want? Just like
forward,
yeah.
You have the map. So it's.
Oh, sorry, the monads.
So no. It is you are using. You said you didn't want to talk about the laws about the functor,
yes.
But you're actually having an example where it's quite easy.
Sorry, is this the wrong slide?
Yeah. So the maybe you had a slide on maybe. Yeah.
This one, yeah.
So it's you using map, but the law is just saying you can say map reverse compose to upper.
That is a great point, and that was originally in these slides, but I thought it was just getting too much, so I took it out. But yeah, that's an example of how these laws can enable you to refactor the code. So using the fact like what we're saying here is that this reverse and to upper, they can be refactored into a composition themselves, right? And the laws of functors or laws of monads or whatever state that this is identical. So as long as our functor follows these laws, we can refactor without having to think too deeply. We're just like, I can extract that and put it in here.
So my point, you can think about it as factor out map, and also the fact that it's an important point that you can reason about stuff, because an important part is to think about these things as something being overloaded. So in the case of maybe functor, it doesn't matter, the result is still the same. But in the case of a list, if you're doing it this way, you can potentially run over a list with 10 elements twice.
Yeah.
So that's 20 times, whereas if you used decompose, like refactor it, it will only be 10.
Yeah. Cool, thank you.
Actually, on the same point, I might be wrong, I'm not familiar with JavaScript, but I feel like given that null is used here to store, the nothing case, here in this case, if reverse were a function that might return a null in case it fails, subsequent maps would get stopped, right? In some way, map would act as bind.
Yeah.
Map can double as bind here because null would be the same as nothing. Whereas if you did
No, maybe contains a null. It isn't a null.
right?
So like this is a bit.
If the function inside the map returns a null, won't it end up being the same thing?
So you end up with a maybe.
Maybe a null wouldn't be the same as null because the null is stored in the maybe. It's not an actual null.
But yeah, I think I see what you're saying is that that would, in the case of a null, that's you're not getting multiple maybes nested inside each other. So yeah, it's kind of applying bind. Is that?
Yeah. Do you mind going back to your implementation of the maybe functor?
Yeah. So if you give it a maybe, you give it a maybe of null, you'll just get back another maybe of null. It's not going to give you maybe of null. So it's kind of performing the join operation as well in that case. It was pointed out in the book actually this implementation of maybe isn't how you see it implemented in libraries, but it's kind of a simpler way to learn to understand what it's doing internally.
Okay. Because if the function right here returns null, it's going to end up being maybe a null.
Yeah.
Right. So
yeah, so you
then
kind
the
of
law
yeah,
actually work, right?
yes.
Figure it out.
Well, because of this implementation.
Yeah, you have to do more checking right here, right? You have to say if this function is null, then
At least
Yeah,
pay
yeah,
attention.
So you spoke about functional programming with JavaScript this time. And for me, JavaScript, functional programming in JavaScript is a no-brainer.
Mhm.
You know, in ES6 and even the functional versions, the community is embracing more and more the object-oriented programming.
Yeah.
Does it still make sense to use functional programming in JavaScript?
I don't know. I guess that's up to you to decide. I mean, like as we saw with the example of, as we saw with some of the examples like currying, the kind of syntactical overhead of that is a lot lighter, certainly with ES6. I still think things like composition. If we go back to that compose example, if we compare this one to that one, I still think this is a lot clearer. So I think that that's a valid concept, and I think that when we're using things like maybe. Maybe can represent that something might fail to return a result and prevent us from having exceptions. So that's giving some of the power of a strongly typed language to JavaScript. So I think there's definitely still uses for it. But I mean, I've got to be honest, when I was looking at all this, some of the stuff I was like, the overhead of that, or the fact that if I wrote that in code that someone else had to use, they wouldn't be familiar with these concepts, probably isn't worth it. But I definitely think it's interesting to explore these things. And with languages like Elm and whatever coming more into the mainstream, I think it's good to have a solid foundation, even if you don't end up using a lot of this day to day. But you can try and sneak bits in, sneak in the odd composition, and see what happens.
Thanks for a great talk. You almost answered my question there, but anyway, you work as a freelance JavaScript developer.
Mm-hmm.
Have you actually used explicit functor or monadic code in your code?
I've not, no. And actually, the code I've been writing recently, I've been using TypeScript for, because getting the compile-time type safety. But what I found when I was playing around with this stuff is that if you're trying to work with Lambda or low-FP, you actually struggle a bit in TypeScript because you have these kind of type definitions which describe the libraries you're working with. And because TypeScript doesn't have concepts like currying at its core, the sort of function definitions you have to write, the type definitions are really unwieldy. And I had real problems actually getting like compose to work sensibly. TypeScript just kind of lost the type. So yeah, I'm yet to actually use any of this stuff, but maybe I'll try. Hi.
Hello, first of all, thanks very much. My question is really a more general question. At the start of your talk, you talked about some of the benefits of the functional approach, like simplicity and understanding what the code does, easily parallelizing the code because there's no dependencies between functions and so on. I wonder if anyone's had a look at the security benefits of code written in a purely functional manner.
I'm sure they probably have in a domain like Haskell, where you can't be impure in a language like Haskell. JavaScript, you can always just escape from this functional kind of world. I don't know, someone else would be a lot better place to answer that than me, to be honest, but I'm sure people have studied that. And because I imagine everything is kind of based on rules and mathematical rules, you can kind of prove that something's secure rather than just going, oh, it looks pretty secure. You've actually got a foundation to prove that.
I guess if I asked the question more precisely, I'd be saying, if I asked the question more precisely, I'd be asking, are there classes of exploit or vulnerability which are not possible when programming using functions?
I don't know. I mean, I guess, if you were using a maybe functor, then you can kind of avoid some situations where you'd be trying to operate on a null value and kind of making it explicit might be a null. And you can imagine, security vulnerabilities in apps where a null value passes through the password check or whatever. So I imagine there could be. And also, like, if you look at this composition, there's kind of like a law about how it works. It goes from right to left, and you're not kind of inventing. If we go back to the example here, we're not going to invent all these steps in between. So first of all, we're writing less code, and less code possibly equals less vulnerabilities, certainly equals less things to type wrong. And also, we kind of, rather than always jumping around, we've got code which is cleaner to read, so it's probably easier to look at, say this for a password validation function. You could look at that and go, right, to go boom, 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 and that looks secure to me, whereas if you're jumping around and doing all this crazy stuff, you could easily miss something. So yeah, I guess the potential benefits there.
Great answer. Anybody else?
It's just to add on. So everybody's using a functor. Like if they use .map, it's the functor. And another interesting point is map is a list is kind of like a maybe. If you have an empty list, nothing happens if you map some function toward the empty list. And if you have one element in it, you only transform that element.
Yeah, so I thought that's something I forgot to mention actually, but like when you're working with an array, you're essentially working with a functor. A bit like, if you're working with a promise, you're kind of working with a functor. If you're working with an array, whichever one does, you're working with a functor without knowing it.
And that's called a natural transformation. Like you can easily go from a list to a maybe and vice versa, but only with one element. And based on the security point, I don't know whether this is true or not, but the fact that it's a functional concept, or most languages have it now. Clojures, they have private state, where sometimes in object-oriented programming, you just have the convention of hiding stuff with an underscore prefix. So,
and I think like actually the implementation, I mean, I copied the implementations of maybe and stuff from the book pretty much, but they could have used a Clojure there to actually secure that inner value. I guess it's because they went on to introduce calling the value inside the IO, but they didn't want to complicate things with that.
The truth was in the forest is in the forest.
Or it should be some private state.
Anyway, any more questions?
Tom, that was brilliant. Thank you very much.
Thank you.
Right, is the pizza here? Yeah, so there's more pizza downstairs. Go and have a drink, and then we'll start getting in what? 8 o'clock? We'll try and.
yeah. But I have so much content. Like I've done many talks also that you can use this in other ways.
Well, I start off together and then I was like such a massive colour stuff that I'm like trying to fit into.
And then want to show your screen bottom. This one. Just entire screen. Yeah.
Yeah, and that's actually one of the things it shows in the book, isn't it? So it sort of puts together like a application.
Is that good?
Like any separate.
Okay, right, I'm going to pop to the little voice room.
Objects like pure and impure, you know, so enforcing that separation.
That's how I got it. So I don't know.
welcome back. A couple of things, well actually just one thing. On Monday next week, we're having the London React meetup in here, into React along. So Ben's going to talk about Haskell in the browser, please on the slide. If you hasn't exploded already, probably will now. Thank you.
So hi everyone. Is that on? Yeah. My name's Ben Ford. I'm currently working at Standard Chartered Bank on the Strats team, which is predominantly Haskell development. So far as at Standard Chartered, I was a CTO at a startup in London where we did basically everything in Haskell apart from in the browser. So that was 18 months ago. If I was going to do the same again, I would definitely use Haskell in the browser. And I'm going to tell you why. Just shut that out for you. Oh, hang on, sorry. I'm just going to give you loads of spoilers right now. What happened there? That was the main one, right. Okay, so I'm not going to talk about how to do Haskell in the browser so much as I'm going to talk about why you might want to think about it. I think Tom actually covered how quite well. All the fundamentals of functional programming were there. So, I mean, so you've probably heard of Haskell. How many people have done any Haskell in the room? I'll just have a quick show of hands. Okay, for those of you who haven't done any Haskell, you've probably heard of Haskell mentioned. Usually, in quite strident tones, it's the best thing ever. So, to discuss why you might want to use Haskell, I'm going to have to recruit the help of a 17th century psychopath. This chap, Miyamoto Musashi. So, Musashi has obviously, even though he's from 1600s, he's obviously done a bit of Haskell because he's obviously tried to learn Haskell before. Now, Haskell's got this reputation of being extremely hard to learn. And it is extremely hard to learn. I learned Haskell by getting up at 5 o'clock in the morning and toiling away for several years before I really understood it. So now he's clearly come across side effects too, and he knows a little bit about immutability. And this is obviously one of the key reasons why we like Haskell, as Tom alluded to before. And anyone who's done a little bit of Haskell, as came up in the discussion actually, is that there's many ways up this mountain. You can map over a composition, or you can compose a bunch of maps, and they have different semantics, but they all get you the same place. Unfortunately, the Haskell mountain has this following property. Everyone read that? Outsiders think the learning curve for Haskell is a cliff. Haskell know it's a cliff with a commit building more cliff on the top. So it's like a constantly moving target that, when I started learning Haskell, even, me, I'm, relatively new at this. Haskell's been around 20 years. The level of stuff you have to learn now is like, every month. So that's a new Haskell extension that you may not see, but you kind of need to understand if you do see it, and then you kind of dive into this hole of learning more stuff. So Musashi's kind of key insights. So I did my usual thing. I'm a lazy Haskell programmer. I didn't actually start writing the slides until 3 days ago. But about 4 days ago, I came across this wonderful quote, which is one of Musashi's quotes. Learn one thing to know 10,000 things. So the question is, which one thing do we pick? In fact, let's just go into a little bit of context there. So I'll read this if you can't read it at the back. If you master the principles, so should probably say Musashi was a swordsman in the 16th century of Japan. And the reason I say he was a psychopath is because basically he learned his craft by going around killing people, as many as he could, and he didn't really care if he, what he did. So I'm not suggesting that that's some sort of a roadmap for your functional programming, but he had a certain focus and purpose. So it says, if you master the principles of sword fencing, when you freely beat one man, you beat any man in the world. The spirit of defeating a man is the same for 10 million men. And this is the key bit. The strategist makes small things into big things. Like building a great bullet from a 1-foot model. I cannot write in detail how this is done. The principle of strategy is having one thing to know 10,000 things. That was me the other day. I was like, what am I going to talk about in in a week? And I read that and I was like, yes, that is it. So which one thing? Obviously Haskell is a smorgasbord of things you could learn. So what should we go for? Mutability. Mutability is very, very important. This means that when we change things, we don't stumble over ourselves. Or maybe referential transparency. This is also quite important. It's related to immutability, but it means that when you're referring to an X, you can pass that X around anywhere, and the X that you get is the same one that you passed. Or monads. Monads are pretty popular. They're hard to grasp because they're so. I think it's because they're so simple. It's you think they must be more complicated than they really are, but they're not. So anyway, the essence of Haskell actually is these things. It's zygomorphic. Zygohystomorphic prepomorphisms. Yeah. Now this is if you climb the top of the Haskell mountain that Ed Komet has built, this is the thing that's right at the top. But I'm going to explain why these things are actually, you can Google this right now. You will not find a single one of these things in the wild, ever, anywhere. But they are the essence of Haskell. Because the essence of Haskell is combining things together, and somewhat relatedly splitting things apart, but I'm going to focus on the one because we've got 30 minutes. So, the basic element of combining things together is the monoid. So, I hope we can see from the little bit of syntax that Tom gave us is that we've got something here which is whenever you see class in Haskell, it's not like class in an imperative in an object-oriented language. Class in Haskell basically says that this thing has certain properties. So a monoid has something that is what we call a zero element, something that doesn't really do anything. It's an empty thing. It has a way of taking something that is a monoid and something else that is the same type of monoid and giving you a new thing that is also a monoid. And given that, we can also do the same thing with lists by kind of lumping them all together until you get to the end of the list, and then you just have one thing. So a simple example of a monoid would be natural numbers, 1, 2, 3, 4, and plus. And in this case, your empty would be 0, the number 0. So if you, so there are certain laws, as Tom mentioned in his talk. So if you add the 0, if you append the 0 element to your empty to one of your monoids, you get the same thing back. So yeah, with natural numbers, obviously 0 plus any number plus 0 is itself. So end up with that. And this is the inputs of that. So okay, so Musashin said, how did he say it? He said, the strategist makes small things into big things. All right, sounds good. So the strategist makes small things into big things, which is important. So this monoid thing, I gave you the example of numbers, but there's lots of other monoids. In fact, they're all over the place. So when I saw this, And then I read that it enhanced kind of knowing one thing to know 10,000 things. Well, you know, this is like the other part of the quote before. So, okay, so what else can we make big things out of from small things? Functions, function composition. Yeah, we've got, so this is the Haskell version of the compose function that Tom showed us earlier. So we take a function from something of type A to something of type B. Then we take a function of something from type B to something of type C, and we get a function of something from A to C. So we go from A to B, from B to C, and we end up with a function that we can apply an A to and get a C from. Yeah, so this is, if anyone's ever tried to learn Haskell recently, they would have come across Bartosh's excellent series, which explains Haskell in terms of category theory. For some reason, he uses pigs in his diagrams, but I didn't want one of those boring category theory diagrams, so I use this one. So, yeah, here's our A to B, then B to C. So when this can be a little bit confusing to start off with. Our A to B is first, so we go from A to B, and then B to C, but the way the compose operation works is you do A to B dot B to C for functions. Anyway, so the strategist makes small functions into big functions. So we've gone from things to functions now, because functions are kind of things as well. And then, well, you know, I'm still going with the concrete panda. And then, so now we're into the meat of combining things together. So when you combine multiple things together, you can be set to fold them down into one. So yeah, we've got this class foldable, which says, you know, we had monoid before, and now we say that, okay, we've got this thing that consists of multiple elements. So you can imagine this is a list, it could be a tree, it could be a graph, it could be a stream, it could be a string of events that happen. And we have, let's see, what's the minimum? Yeah, so the minimum kind of implementation of this thing is we fold everything into one. And fold map, well, fold map is actually implemented in terms of a monoid, because we've got this thing that takes each list element to the monoid, and then we just collapse them all down. And then we've got this horrific thing here. What on earth is all this? Well, this is just another way of saying that I want to treat this thing as a monoid. So this is a function, f. F is here, it's this a, b, b. And this is just a way of collapsing that into another thing that composes with other things different. So we collapse this, we fold map over it, which is we collapse them all down into one. And then this is just saying take it back out. Get me the original thing that I asked for, which is one of these Z things here. Yeah, okay, Z. So Z's here. Okay, so, and then all of this other stuff drops out naturally, which is just different ways of saying I want to combine stuff together. So we've got, yeah, bonus is fold left, fold right. And this, yeah, this is even more weird. But this is just another way of saying, okay, we've seen compose before, this is just grouping functions together. This is just saying I'm going to flip. Flip is on the function level, so I take something that's from A to B and I take it to B to A, so that here our functions around the wrong way. So we flip it here, and then we unflip it here, and then we fold map, and then we extract this, and we extract that, and we just basically completely turn the evaluation order of our function, sort of hand waving. And this is the endover. So this is the thing that basically takes a function. Now it has to be a function that goes from the same thing to the same thing. And what we do is we just compose. So this is just saying like a different way of saying compose, which is a different way of saying combine. Okay, and this is actually in the documentation, in the comments, to kind of somehow explain this to everybody. The monoid of endomorphisms under composition. Everyone get it? Good. And that's why Haskellers say this. Anyone heard this expression before? Yeah, it's, you know, the kind of the quintessential Haskellers talk a bunch of nonsense phrase. Well, yeah, it's actually true. It might be nonsense, but it's true. And now, so we can take these ways of mapping things together, and we can actually do this to effects. So I'm not going to talk about monads at all, such. But we can take what a monad signifies, which is an effect in the real world, and we can actually apply exactly the same tools. So fmap is your functor map, and look at this. This thing is implemented in terms of that thing, because they all kind of do the same thing. So keep in mind this function here. So we've got something which has elements, and we've got something which indicates that you can combine stuff together. We take our container of elements, we apply this function to each one, and we produce something that can be mapped together, and then we end up with the thing that can be mapped together and a container of these things. Okay, quite weird. Let's see where that takes us. And okay, here's an even more clear example that we're talking about the same thing with everything we do. So fold R was this thing from before. Pure is the 0 element from the monoid. F is the function that gives you the thing that can be composed together. And this thing just says, okay, I don't care what's in it, I just want to do the effects. I just want the side effects of what that does. So this is like your visitor pattern. And yeah, if you want to get a really good understanding of how this all fits together, because there's, you know, I've just basically scratched the surface. There's a huge body of theory about why this stuff all works. Best introduction is probably practical recursion schemes, and you know, you will almost certainly bang your head against this for, you know, several months, I would say, if you decide to go for it. Okay, so examples of this. So in Haskell, there's a library called pipes, which is basically you have something that can produce or consume elements. So you know, ignore all these things. But we're basically saying, okay, we've got a pipeline of things. We've got things coming out of this pipeline of type B. We've got a function here to transform those things into type C, and we end up with a pipeline of things that are type C, which is our thought from our traversable element. You know, we've got our traversable, we've got our function that maps over the things inside the traversable, and then we end up with a traversable of a different type that we can treat exactly the same way as our first traversable. Yeah, which is written another way, this. So the one difference is here that this one is kind of collapsed. And the reason is that this proxy type here, it kind of subsumes this concept of something within something. And I'll explain how that sort of pans out later on. But yeah, I like that. Okay, so you know, I said this was about Haskell in the browser, and I haven't talked about the browser at all. So okay, so we've got a few things in the browser that we can use. Reflex is a functional reactive programming library, and you know it's pretty approachable. We've got, you know, that makes perfect sense, right? We've got a widget thing. Now, yeah, it doesn't make any sense at all. I've never done any reflex, but I can read a few things out of here that give me some idea how it works, but it doesn't make any sense whatsoever. But neither does that. But we apply exactly the same logic that we did with the foldables and everything else. All this thing is saying is that all of these things are available within this. So we're making small types into big types. Okay, you'll be glad to know I've run out of Country Panda reaction pictures. But we've got exactly the same stuff underneath, right? We've got for, yeah, we've got something that contains something. We've got something that maps whatever that is into that, and then we end up with something containing one of these. we've got some way of applying, excuse me, we've got some way of folding. So we've got A, we've got something that comes in, we've got the existing state, and we produce a new existing state. We start off with the 0 state, the first state, we give it events of this, and we end up with one of these. And this just, you can combine all this stuff together in user interface workers. And then, so this is part of this, goes back to the effective thing I was talking about. I'm not sure explain that one. But here it is kind of in action. So, yeah, this is our monad. Yeah, we're taking something that is a number input. We're taking something else that's a number input. We're taking something here, which is an operation, and then we're just applying them. Oops, sorry. So we're applying this, and we end up with our result, and then we map our result into a UI element, and we display it. And this whole thing here can be explained in terms of all the types that we looked at earlier. And then, so I had a little play with, I've done no Haskell in the browser. I had a little play with the library that I wrote. So here's our fold function. Yeah, we've got actions. So these are events that happen. We've got our state, which is, items. And then we've got something that takes a channel of these actions that we can map over and change. And we take our state, and our state is rendered into HTML, just like React, exactly the same. And then our model is an action, the event type that we expect, our state, the state type that we expect. And in this case, the action is the same, but you might conceivably want to have a different event type coming out of the UI. So you might want to, so this event type is the event type that goes into the model, this one. But you might conceivably want to have a smaller thing that you then combine up and you multiplex everything together from different components. And then we've got our 0 element, which is this guy. This is a very simple component, so it doesn't have any initial kind of environment that it needs to read, which is that. And there's our component. That's, this is exactly the same as how Flux works, except it's in terms of all the foldable environment stuff that I mentioned earlier. And then, yeah, that's there. And then we've got PureScript. So PureScript is a Haskell-like language. It produces smaller output than GHC.js, which was the previous example. And it's kind of greenfield. What would functional programming look like if you wanted to do, a layer over JavaScript that was kind of easy to understand, didn't produce huge output, and was strict rather than lazy. So this takes this whole idea of composing things together and collapsing things to a whole nother level, because in here we have this thing here, which is, as Christian mentioned earlier, whenever you see natural, it means that you're going to have something that looks really simple but is actually quite hard to understand, natural transformations. But the idea here is that instead of my previous on action, which is just what am I going to do, this one also has the idea of querying the state. So you might want to, you've got your big state object, you might want to pull a little bit out of it to look at. But it's exactly the same stuff, right? We've got our component with a state and a query. Now, query in my world was an event that in the on world was an event that would change the state. Well, this is just an event that can change the state or pull something out of the state. So here's our kind of, this is our HTML element as you might do in React. And on click, we're going to say, okay, right, this is the toggle state action. And then down here, we say, okay, I'm evaluating, using pattern matching, I'm going to say, okay, what am I going to do when I get a toggle state? What am I going to do when I get state? And the one kind of extra little bit here is this continue or next. And you'll notice that what we do here is this is basically collapsing something down again. This is exactly the same as fold. There's nothing different here. All we're doing is, instead of collapsing a kind of a small structure. We're collapsing a nested structure. So that's what this thing is. That's what this thing is. This is just saying, okay, I've done my bit, do what else you want. And this guy here, well, this is easy. This is just like get me what the current state is. And then see we've got this continue. So on is a Boolean. So that's a Boolean. Continue is a function that takes a Boolean and then just continues with the rest of the world. So we just say, okay, right, I'm done. What else is there? And this is actually, so this is a UI library, but this concept is exactly the same as the one that the pipes library of event streaming that I mentioned earlier is implemented upon. So we have it, and another example of combining things being the fundamental underlying abstraction that we work with. So, in conclusion, yeah, look for the fundamentals. You know, these concepts are not unique to Haskell. If there's any people that do Clojure or Clojure here, there's a library called Tessa, which is an analytics kind of library, MapReduce, and it's a multi-level MapReduce. It's all implemented on the idea of functors and folds. The UI stuff that we've looked at, this is basically what React and Flux is underneath. I mean, these are the fundamentals of what those things are built on. That's why they work so well. That's why they're good. And when you find one, you know, keep going until you get to your zygomorphic prepomorphism things. Sorry?
Zygohistomorph.
So, what is zygohistomorphic prepomorphisms? That's the one. Yeah. Keep digging, right? There's, you know, as you discover one abstraction, you'll keep going until you discover other abstractions underneath, until you get to the kind of the little compositional pieces that fit together. And then, you know, a couple of little Musashi quotes that I quite like. Yeah, this is learning this stuff is it's pretty soul destroying at times. You know, you're like, why the hell am I doing this? Like, why am I up at 5 o'clock in the morning to zygomorphic thingy myself? And actually, it's because there is a structure underneath all of the programming that we do that's actually really very, very interesting. And as you discover more of it, you just discover new vistas that open up. And I think it's highly, highly worth your time. Because the purpose of today's training is to defeat yesterday's understanding. And that is, if you know, I'm gutted that I only found this quote like yesterday, because this basically defines the reason that I learned Haskell. My process learning Haskell is, okay, Haskell is all computer science papers. I'm going to read a computer science paper, and I'm going to feel like an idiot. And I'm going to measure my progress by how much less of an idiot next time I feel next time I read this paper. And that is, you know, the idea of, if you've ever read Carol Dweck's book Mindset, or the concept of deliberate practice, that's it, basically, the ability to come back to things when it makes you feel bad. It's also quite useful for learning martial arts, as Musashi understood. And it may seem difficult at first, but everything is difficult at first. Everything worthwhile is difficult at first. Okay, yeah. If you actually want to check these out, you can look at the slides and you can go here and you'll discover just how useless this thing is. But it's important to, you know, I used it as a kind of a bit of a bait and switch, I suppose, is that, you know, you can follow this rabbit hole as deep as you want, and, you know, almost everyone except their command loses interest before they get to zygohistomorphic prepomorphisms. But some people even go there. Practical recursion schemes, I highly, highly recommend reading this. It's very, very approachable, much more approachable than my talk. And this one too. And then if you're really interested in looking at, you know, I'm not going to tell you how to set up reflex because it's a very moving target. Pure scripts perhaps marginally less moving. And these were my little experiments with sort of type channels in the browser. Any questions?
I have one that's a bit of a pointed one, sorry about that. So a lot of these reasons that you gave are, I think, really good reasons to learn Haskell, but I didn't quite get why would I learn Haskell in the front end except Haskell is the best. Like, is there anything that today you can actually gain using these tools?
So I would say that PureScript is well worth using. I think. Okay, it depends. Let me back up. So it depends what you want out of it, right? If this is a personal learning exercise, perhaps not. If it's a tool to enable you to hire a good team, perhaps so. If you've got some guy on your team that has taken the trouble to learn this and says, you know, we could build better stuff with it, maybe. One thing I found with these abstractions is because they're so structured, is that you can hire a bunch of people around one good person that understands all this, and they can kind of help you fill in the gaps. And you know, even though I was a CTO at a startup where we used Haskell, I was actually that guy that filled in the gaps. It's extremely useful for attracting the right kind of people. Yes, in reality, you know, mainstream stuff has a lot of these things, but I guess maybe one of the reasons that I would suggest to learn Haskell anyway is that this is where you're going to understand what is happening underneath. So, you know, if you've got that drive to really figure out why your microphone makes loads of noise, then, you know, go for it and dig in.
Thanks.
Very nice. Okay, thank you very much, Ben. That was brilliant. Thank you very much. Okay, big thanks to Tom and Ben for talking, to Skills Matter for hosting us. If anybody wants to give a talk, this meetup, you've been more welcome. See you next time. We're going to head a consultant. Thank you.